Here's starting the last little bit of chapter 9. The last little bit will still use the tests that you learned in the first half of chapter 9, not in all of the sections, but you still have to remember those first tests. So it's kind of a tough time to do this because part of this test or this chapter will be after spring break, so that does make you remember those tests for a significant amount of time. But it's also good, I guess. You need to know them for the final too, so it's not a bad thing, but it does get to be pretty extended because this portion of the test will be after spring break. The objective for 9.7 is it's called Taylor and Maclaurin polynomials. So what the Taylor and Maclaurin polynomials do, we're going to write a function as a polynomial, and so and then we can use that polynomial to approximate a function. So we want to write polynomials. And if you think of a polynomial, we're going to call our polynomials p of x, and whatever degree it may be. You could have ax cubed plus bx squared, and all these could be plus or minus, plus cx plus d. This would be a third degree polynomial. We'll write a first degree polynomial would just be the equation of a line. A second degree polynomial would be quadratic, a third degree polynomial, fourth degree polynomial, etc. And we are going to write polynomials to represent other elementary functions. So what this basically means is that this means we are going to write f of x, which is equal to e to the x. Obviously that is not a polynomial, but we're going to write this function as a polynomial. And the higher the degree it is of our polynomial, the more accurate it will be as a representative for that function. So what has to happen is you have to choose a number c in the domain of our original function, at which our function and the polynomial will have the same value. And this c value is going to be given to you. So this c value will be given. Oops. That is basically your point of tangency. So if you look below, here I'm going to have my function, which is the black line, the black graph, and I have this point of tangency. I'm going to create a polynomial coming from that point of tangency, so that has to be given. The approximating polynomial is said to be expanded about c or centered at c, and so that point is very crucial. And again, it's going to be given so that everybody has the same value, and usually it's a fairly convenient value to work with. So looking at this graph, a couple of things. F of x is the original function. This original function is not a polynomial. It'd be like e to the x or sine x, cosine x. It could be natural log x. It's something other than a polynomial, but it's a pretty basic elementary function that we're used to. Then what we want to do, put a little arrow there, is we want to find a polynomial and that polynomial we're going to call p of x to approximate the function. And then, like I said before, the higher the degree, the more accurate the polynomial. I'm just going to write the more accurate. Maybe a better word instead of saying the more accurate the polynomial is, it's the more accurate is the approximation. And obviously making a higher degree is going to take more work too, and so there's some extent where you don't want to do this anymore either. So we're going to start with a pretty easy example in order to figure out how this all works out. And so for our example, we're going to use that function e to the x. So here's our function, f of x equals e to the x. We're going to find a first degree polynomial function. So here's our first degree polynomial, which obviously it's x to the power of 1. This is the equation of a line because it's a first degree. But specifically when we go through this, we're going to be looking for a sub 0 and a sub 1. And then we need to find those values when we're solving. So we want to find a first degree polynomial whose value and slope agree with the value and slope of our function at x equals 0. So x equals 0 is that c value that I was talking about that they have to give us. So we are centered about, or we're expanding about, x equals 0. So what we want to do is we have to make sure our value and our slope agree. So if we start with it, we can say, well, here's our the value. And we have f of x equals e to the x is our function. We're expanding about x equals 0. So then when you plug in 0 into the function, we know that our value has to equal 1. We also have to show that our slope is equivalent. And so here's our original function. I'll write down slope so we know what we're doing here. In order to get slope, well, how do you get slope? We take our derivative. So we have f prime of x. Our original function is e to the x. The derivative of e to the x is e to the x. And we want to calculate what is our slope at 0. That's that point that we're expanding about. So then here's our e to the power of 0. That is also equal to 1. Well, what we have to do here is that we have to make sure that our polynomial and our original function, that their values and their slopes agree. So here's our original function. Now we want to go to our polynomial. So maybe we can say here's f of x. Here's our polynomial. And try to keep your spacing similar to what I have because we're going to write some more down here. If we start with our original, or our function, and it's a first degree polynomial, we have a to the a sub 0 plus a sub 1 times x. Well, if I take for the slope of it, the first derivative, the derivative of a sub 0 is 0, plus in this situation we're just left with a sub 1. Well, I know that this slope has to equal 1. So if this slope has to equal 1, when I plug in a 0 into this thing, no matter what, if my slopes are going to be equivalent, a sub 1 better equal 1. So that allows for us to solve for that first constant a sub 1. The other thing that we have to solve for is for our values to be the same. And if our values have to be the same, if I take my original polynomial, so a sub 0 plus a sub 1 times x, for our value, when I plug in a 0, this answer, so up here if I looked at my value of it, in this situation, when you plug in a 0, it has to equal 1. Okay, well when I plug in a 0, it has to equal 1. If I plug in 0 for x, that's going to give me a 0, even though I know that this a sub 1, I guess I probably could have written that as a 1, or not put anything there. Therefore, that tells me that if this thing has to equal 1, a sub 0 also has to equal 1. So my first degree polynomial, p of x, is equal to 1 plus 1x, and I'm just going to write it as x. We'll put a line underneath here. This is our first degree polynomial. Well, let's say I want to expand this and make it a second degree polynomial because I know a second degree polynomial is going to be more accurate. If I want a second degree polynomial, so second degree polynomial, that's going to look like this, where a second degree polynomial, and then they start putting a subscript there of a 2. A second degree polynomial is written as our a sub 0 plus a sub 1 times x plus a sub 2 times x squared. So it's a second degree polynomial, it has to be squared. So since it's second degree polynomial has to be squared, what ends up happening now is that your second derivative of your function has to equal the second derivative of the polynomial. And so that's, and as you continue, obviously that can, if you want a third degree polynomial, the third derivative of your original function has to equal the third derivative of your polynomial. So how that looks here is, if I look at my original function, f of x equals e to the x, and I have to get my slopes to match up, well then f prime of x we know is e to the x, and f double prime, or the second derivative of x, also is equal to e to the x. I'm still centered around 0, so when I plug a 0 into this function, or into the second derivative, I know that this answer is equal to 1. Well, this has to be the same. So when I look at my polynomial, and my polynomial a sub 0 plus a sub 1 times x plus a sub 2x squared, when I take the first derivative of that, the derivative of a sub 0 is 0. The next term is going to give me an a sub 1, and the derivative of the third term will give me 2 times a sub 2 times x, and then obviously to the power of 1. Well, I need to take my second derivative, so the second derivative of the polynomial. That first term, the derivative is 0. This term, the derivative is 2a sub 2. When I plug a 0 into this function, I have to get the answer as 1. Well, if I plug a 0 into this function, or into the second derivative, there's really no place to plug it in. So in this situation, it's still just 2a sub 2. Because I don't have an x there, this thing, though, has to equal the same thing as what the derivative up here, the second derivative of my function. So this has to equal 1, which therefore tells me that a sub 2 is equal to 1 divided by 2. And that solves for my coefficient. The nice thing when you keep writing polynomials is that the terms stay. So if we're going back up, that first term of a 1, that's always going to be your a sub 0. A sub 1 is always going to be x. So then you just keep expanding your terms from there. So my second degree polynomial, I still keep the 1, I still keep the plus x. Now, the coefficient in front of my x squared, because it's the second here, would be 1/2 x squared. And we can continue this process. Similar situation if I want a third degree polynomial. So third degree polynomial. Remember, these first three terms from your second degree polynomial have to stay. Those are not going to change. So if I go back, well, here's the second derivative from my original function. If I want a third degree polynomial, I need to take the third derivative from my original function. Well, this is a nice easy one. So the third derivative is e to the x. I'm centered at 0, so when I plug in a 0, e to the power of 0, I get 1. This derivative, the third derivative of my original function, has to equal the third derivative of my polynomial. Well, if we look at a third degree polynomial, we're going to have a sub 0 plus a sub 1 times x plus a sub 2 x squared plus a sub 3 x cubed. And I already know what this term is, what this term is, what this term is, but I am going to go through all this to solve for my a sub 3. Well, as I take my first derivative again, so rather tedious here, that term is going to simplify out. I have a sub 1 plus 2 times a sub 2 times x plus 3 times a sub 3 x squared. My second derivative for my third degree polynomial, first term is going to be 0. This term, the derivative, is 2a sub 2 plus the derivative of this term is 6a sub 3 times x. Now as I look at the third derivative of my third degree polynomial, this is just a constant, so the derivative is 0. The derivative of this term will give me 6a sub 3. Remember, when I plug in a 0 into the third derivative of my third degree polynomial, well, if I plug in a 0, I don't have a variable there. This has to equal the same derivative the same thing as the third derivative of the original function. Whew, that's a lot. So this has to equal 1. Therefore, a sub 3 is 1/6. And from here you could predict, obviously, what the next, if you wanted to have a fourth degree polynomial and etc. But our third degree polynomial then, the terms stay the same, or the first three do 1 plus x plus 1/2 x squared, and then we'd have our plus 1/6 x cubed. So here is our approximation if we want a third degree polynomial. This is a fairly decent approximation for the function e to the power of x. And we are centered at 0, so I want to take points fairly close to 0. The larger the degree of my polynomial, the more accurate it is going to be farther away from 0, but I really have to be still fairly close to 0 for this to work. But again, it's just writing a polynomial in place of a function. Well, what's nice about this is there's definitely a shortcut that makes this a whole heck of a lot easier than writing all of this out. You'll still have to write parts of it, but there's a much shorter way. So a Taylor polynomial and a Maclaurin polynomial, there's a slight difference between them. Our Taylor polynomial, our function has to have n derivatives, which you'll be able to take multiple derivatives of it at c, so you can't have a derivative equal to 0. Then what happens if you're writing a Taylor polynomial? So we have a polynomial to the degree of n, whatever the question asks it to be. What this is equal to is our function at c. So plug it c into the original function, and that's basically if you have a 0 degree polynomial, that point just has to match up. Then it would end up being, the formula for this is take the first derivative of my original function, plug in c. We have to multiply that by x minus c. That's to the power of 1, which technically you don't have to write, but you'll see a pattern here, so we're going to keep it, divided by 1 factorial. The next term, if I wanted a second degree polynomial, because this would create your first degree polynomial, it's to the power of 1, divided by 1 factorial. A second degree is take the second derivative of your function, plug in c, that centering point. That's going to give you a coefficient, a number. Multiply it by x minus c, that's squared, divided by 2 factorial. And we can continue this, so the next term would be take your third derivative of your original function, plug in your centering point, so plug in c, x minus c to the power of 3 divided by 3 factorial. And you can continue this to, let's say, the nth degree polynomial. Well, you'd have to take the nth derivative of your original function, plug in c, so that's going to give you that constant. Then you have x minus c to the power of n divided by n factorial. So you still have to go through and calculate your derivatives, but much more efficient than than going through everything by hand. The difference here between a Taylor polynomial and a Maclaurin polynomial, a Taylor polynomial, our function has n derivatives at c, where c is going to be some number and it's other than 0. C is equal to a number other than 0. Well, a Maclaurin polynomial is just a really specific type of Taylor polynomial. And again, you're going to have a function, you have to be able to take n derivatives of your original function. But in this situation, c has to equal 0, so you're centered about 0. Then for our Maclaurin polynomial, specifically instead of having a c, you're just going to have a 0 there. So what is your original function at 0? Plus, you still have to take your first derivative. You're going to plug in 0 to get that constant. Here, though, we don't have to make it x minus c anymore. It's x minus 0, which is just going to be x. So that would just be x, technically to the power of 1, even though you don't have to write that in, or you shouldn't because it kind of looks ugly, divided by 1 factorial, which again, that's kind of tedious to write too. But just to show the pattern here. Plus, take the second derivative of your original function, plug in a 0, All right, then that would be x squared, so this is my second degree polynomial, divided by 2 factorial. Plus, take the third derivative of my function, plug in a 0. That's a coefficient, x cubed, divided by 3 factorial. And you could have an nth degree polynomial. So the nth derivative, plug in 0, x to the power of n, divided by n factorial. So much more efficient, and to remember the formulas, and after you do a couple, they're really easy to remember. All right, so a couple examples here. You want to find a Taylor polynomial. Actually, we have to find 5 Taylor polynomials. Our 0 degree polynomial, our first degree, second degree, third degree, fourth degree polynomial. Our function is natural log of x. So obviously that's not a polynomial. We're trying to write a polynomial in place of natural log of x. And here it's centered at x equals 1. We can't be centered at 0 because natural log 0, it's not part of the domain, it doesn't exist. Once we're done with that part, so that's kind of our A, then for B, we're going to use our 4th degree Taylor polynomial to approximate the value of natural log of 1.1. And could you plug this into your calculator? Yeah, absolutely you can. But let's say you don't have a natural log button or key. Here's another way that you can do it, and you're just showing that, okay, this is an approximation for this particular function. So usually what I end up doing here is if I have to make a 4th degree polynomial, I rattle off my 4 derivatives right away. Because a 4th degree polynomial, I am going to need the 4th derivative. So I start with, well, here's my original function, f of x equals natural log of x. And I always start with your original function because that first term is included. So don't jump right away to the derivative. Start with your with your function. Well, then my first derivative would be 1 divided by x. The second derivative, technically now this is x to the negative 1, would be negative 1 x to the negative 2. So negative 1 divided by x squared. My third derivative, so remember this is equivalent to negative x to the negative 2, would be 2x to the negative 3. So 2 divided by x cubed. And my fourth derivative, if you get stuck, don't make a foolish mistake here, it's going to be real bad from there, would be equal to negative 6 divided by x to the 4th. So write out the cheating, you're not really cheating, but write out that extra step if you need to so that you don't screw up with your derivatives. Otherwise, if you get your first derivative wrong, you're in trouble for your 4th derivative. Well, now we have to figure out the value of all of these things at where x is equal to 1, so where we're centered. And so that's why don't skip that original function. Make sure you write that in your step, although in this one, natural log of 1 is just equal to 0. For your first derivative, if I plug in a 1, I'm going to get, instead of x, I should put a 1 here. I'm going to get 1 divided by 1, which is 1. In the second derivative, when I plug in a 1, I'm going to get negative 1. In the third derivative, when I plug in a 1, I'm going to get a positive 2. And in the fourth derivative, when I plug in 1, I'm going to get negative 6. These coefficients are all used in our formula when we expand our formulas. So our 0 degree polynomial, 0 degrees, this would just equal 0. Then for our first degree polynomial, remember you add your previous terms, so this technically should be 0, although it's not going to matter. Plus, here we have our 1, so our coefficient is 1 times x minus 1, because we're centered at 1. That's to the power of 1 divided by 1 factorial. And you should always simplify, so you definitely don't want to write all this stuff in. It's much better just to make it, or to rewrite this as just x minus 1. That's a lot nicer. So then our second degree polynomial, we have to have our previous terms was 0, and we simplified this down now, so it's just your x minus 1. And we're going to keep writing all of this. Plus, now we go to the coefficient that goes with our second derivative. So it's a negative 1, so I'm going to make that a negative 1 times where you're centered, x minus 1. It's a second degree, so it's squared, divided by 2 factorial. In the third degree polynomial, keep the 0, so I have 0 plus, keep the x minus 1, minus, if I simplify this, I would have x minus 1 squared divided by 2, and then for my third degree polynomial, my coefficient is a positive 2. That'd be x minus 1 cubed, because it's a third degree, divided by 3 factorial. And our last one, our fourth degree, I'm not going to write in 0 because I don't want to have to rewrite another step to clean this up. So 0, it's not worth writing. Then we have our x minus 1. Our next term is x minus 1, that quantity squared, divided by 2. Our next term is going to be positive. 3 factorial 6. So 2 6 will give us 1/3. X minus 1 to the third. Then our last one, we'd have negative 6. And then that's x minus 1 to the fourth divided by 4 factorial. Well, we know 4 factorial is equivalent to 24. 6/24 is going to give us 4. So as we simplify it, we can just say that our answer, or this last term, x minus 1 to the fourth divided by 4. And this one, obviously, it's kind of nice. You can see a pattern with it. So that's really step A, or part A. We wrote out 5 polynomials. And then the last part for B, use the fourth degree polynomial. So we have to use the fourth degree polynomial, to approximate the value of natural log of 1.1. Basically then, in place of x, you're going to plug in a 1.1. So take your calculators out, and as you go through this, it's pretty quick to evaluate, because you're going to have that 1.1 every time. Well, minus 1 is just going to give you the 0.1. So you can just go through there and say it's that 0.1 and quickly calculate things. So it would give you 0.1 minus 0.1 squared divided by 2. Then it would be plus 0.1 cubed divided by 3. And then minus 0.1 to the fourth divided by 4. And when you calculate it using your polynomial, so we could say our fourth degree polynomial at 1.1 is approximately 0.0953. And if you actually plugged it in, natural log of 1.1, if we look at this is 0.09531. There's a slight difference. I'll always make sure I can tell if you use the exact or if you use the polynomial, so make sure that you use the polynomial to plug it in. But just keep in mind that this is approximation, and obviously this is a really good approximation. You're only a tenth away as well, so it's not like you've moved too far. If I asked you to approximate 1.5, obviously it's going to be a little bit more, it won't be quite as good of an approximation, a little bit more off. All right. 2 more here, and we'll a little bit quicker. They won't take quite so long, but we want to find the third degree Taylor polynomial for f of x equals sine x. So sine x is obviously a trig function. It's not a polynomial. We're expanding about pi over 6. So we don't have to go through everything of finding your first, your second, everything right away. We just want to jump right to the third degree. You still have to figure out what are the values of the derivatives, the first derivative, second derivative, and third derivative at pi over 6. So don't forget, start with your original function. Take your first derivative. Take your second derivative. And your third derivative, negative cosine x. Then you're plugging in that centering point into each thing. So I want to evaluate my function at pi over 6. Sine of pi over 6 is 1/2. I have to evaluate the first derivative at pi over 6. Well, cosine of pi over 6 is square root of 3 over 2. I want to evaluate the second derivative at that pi over 6, that centering point. That brings me to negative 1/2. And I have to evaluate the third derivative at pi over 6, which has negative square root of 3 over 2. Well, now as I write my third degree polynomial, here's your first term is 1/2. Your second term it's a positive, it'd be square root of 3. I have to divide it by 2. In the numerator, I'm going to have x minus pi over 6. That's to the power of 1, which I'm not going to put in, divided by 1 factorial, which is 1. And just scoot my 2 over so it looks nice. For the second degree, so minus, I'm not going to put a 1 in there, it's not worth it. I'm going to have x minus pi over 6. It's the second derivative, so that's squared. That 2 should be in the denominator. It's times 2 factorial, so this denominator would be equivalent to 4. The next term, it's negative. My coefficient is square root of 3 over 2. My center is at x minus pi over 6. This deals with the third derivative, so it's cubed. So if you ever get stuck, that's an easy way to remember. Divided by 3 factorial. 3 factorial is 6 times 2 will give us 12, and we can just erase it, call it 12. So it's pretty quick and efficient when you don't have to go through creating the first, second, third, fourth. That's rather annoying, but you can create a third degree polynomial very quickly. Make sure that you find the coefficient, so that's this portion over here. Do not forget to include that original function. One more, a third degree polynomial, or Maclaurin polynomial. Technically, I don't ever remember the difference between Taylor and Maclaurin. If it's a Taylor polynomial, you're not centered at 0. Well, they have to tell you where you're centered. So if they tell you where you're centered, obviously you're going to use that. If they don't tell you where you're centered, then it's a Maclaurin polynomial, and that's how I know, like, okay, well, they didn't tell me. That means that it's Maclaurin, and then you're centered. Your C value would equal 0. But really, there's no difference between the two of them then. All right, so I want to find my third degree polynomial. You have to be very, very careful with your derivatives and your chain rule and your product rule. And that's what ends up getting us in some of these, is that we really forget to use both rules, the chain and the product. So we have e equals 3 to the x. Our first derivative of this, remember the derivative of e is e to the 3x, it stays. Your chain rule, what's the derivative of 3x? Just a 3. For your second derivative, you do not need to use the product rule now because 3 is just a constant. So you keep the e to the 3x. The derivative of 3x is 3. You have that other 3, so that'll give you a 9. And then your third derivative, e to the 3x times 3 will give us 27. What is the value of the function at 0? Well, e to the power of 0 will give us 1. What is the derivative at 0? That will be 3. The second derivative at 0 is 9. The third derivative at 0 is 27. So those are pretty slick and easy. When you write your Maclaurin polynomial, it is a third degree, so it's nice to note that. Start with your first term, that's 1, plus this 3, it's my first degree, so it's x, technically to the power of 1 divided by 1 factorial, plus 9, x squared divided by 2 factorial, which is just 2. My third degree will be with the third derivative, 27, x cubed divided by 3 factorial, which is 6, and that's kind of nice from there. So not too bad. I guess you should probably simplify that part of it. So if you have your 27/6, it's probably a lot better to write that as 9/2. That's not too bad to quickly change. So Taylor and Maclaurin polynomials, and just creating them. Your homework assignment for this is pretty short. what is that, eight problems in there. So I hope this is a good one. That beginning stuff I know was a little bit confusing, but really I did that so that like I have to take the derivative. If I want a third degree polynomial, I need to take the third derivative of my function, which would be equal to the third derivative of your polynomial. So good luck with this, and yeah, get this homework done for tomorrow. It's a short assignment, so you'll build on these things on your Taylor and Maclaurin polynomials. So for these 8 problems, they should definitely be done by tomorrow. Have a great day.